Let's talk about acetals and ketals. Acetals and ketals, they're fundamental to carbohydrate chemistry. Acetals and ketals also occur in natural products, and they're important protecting groups in organic synthesis. First, a little functional group vocabulary. Ethers have one alkyl or aryl on either side of an oxygen. In other words, one OR group on one carbon. Ketals, on the other hand, have two OR groups on one carbon. Acetals are formed from aldehydes, and ketals are formed from ketones. Importantly, when there's one OH group and one OR group on a carbon, then this is a hemiacetal or a hemiketal. It's a hemiacetal if it's formed from an aldehyde, and it's a hemiketal. This is formed from a ketone. Let's revise this using acetals as our point of reference. Acetals have a hydrogen and an alkyl group on a central carbon bearing two OR groups. Acetals, of course, are formed from aldehydes. Hemiacetals have one OH and one OR group on that same carbon. Hemiacetals are the halfway stage between acetals and aldehydes. Now, it's critical to know the mechanism of acetal and aldehyde formation. If you don't know that, you can't understand carbohydrate chemistry. To illustrate what I mean, look at this picture of glucose. The functionality in green is a hemiacetal. All the other OH groups around the circumference of the molecule are alcohols. But that one on the anomeric carbon, we call it, is a special one. That's a hemiacetal. If I form a dimer of glucose with the oxygens in this orientation, note now the green oxygen atoms have changed. They're no longer a hemiacetal functionality. They are a full acetal. Acetals can link carbohydrates together. Similarly, if I make three glucose in a row, that's a trisaccharide, they are linked by two acetal functionalities, and one hemiacetal is on the end. Said differently, what connects the three glucose groups together? It's two acetal functionalities. So two acetals connect three glucose units. And we could go on. We could look at a tetramer of glucose. It's connected by three acetal units, and on the end is a hemiacetal. And in the extreme, we could polymerize it to get cellulose. Cellulose is a constituent of plant cell walls. So to consider the key steps in the mechanism of acetal or ketal formation or acetal and ketal hydrolysis, let's begin with this simple ketal. We want to get to the corresponding hemiketal. So somehow we have to lose a molecule of methanol. And the catalyst for this reaction is protons. And then we have to lose the other methoxy group, again, catalyzed by protons. And that gives us a hydrate. They collapse, they lose water, and generate a ketone. The overall process then, ketal, hemiketal, hydrate, ketone, is an equilibrium. And it's influenced by how much water we put in or how much methanol we put in. We can determine what the resting point of the equilibrium is. If we do the reaction in water or with a large excess of water, then we bias the equilibrium towards the ketone. But if we do the reaction in the presence of methanol and acid, we bias the equilibrium towards the dimethyl ketal. Ideally, we'll do the reaction in dry methanol to get this to work. The reason for this is just the equilibrium constant. A large excess of methanol or water will push it one way or the other way. This is Le Chatelier's principle in old-fashioned chemistry. but it's just really the K value for the equilibrium. And don't forget the intermediates that we have to go through to get to either end. Okay, we're ready. Let's look at the mechanism. This ketal is symmetrical. Let's choose a victim, one O methyl group to leave. Arbitrary. Because it's going to leave, we'll protonate that one. And then we get 3 bonds to oxygen, an oxonium ion. And now the key step in the whole process. It's key because both oxygens work together. The one that's going to remain pushes in a lone pair, and the one that's going to leave departs as methanol. The protonation helps break that bond, and it's assisted by the oxygen that's staying. And that's why cleavage of ketals and acetals is easier than acid-catalyzed cleavage of ethers. So here's our oxonium ion. And of course, that's a superb electrophile. And if we have excess water in the equilibrium, water is the nucleophile that will add to it. When it does, the OH2 fragment becomes an oxonium ion. Well, we don't want to make it leave again. We would just arrive back at where we started. That happens, but it's boring. So let's take off a proton, and after loss of a proton from that methoxy group, we have arrived at the halfway stage, the hemi-ketal. We're over the hump now. All we've got to do is make the other methoxy leave. And we do that, of course, by protonating it. Let's just recap. The key step in this process is that push-pull intermediate, the tetrahedral intermediate. And then the oxonium that's formed is attacked by the nucleophile, water. And finally, deprotonation gives us the halfway stage. So in theory, you may think you understand this mechanism, but in practice, you probably don't until you've tried a varied set of substrates. Let's try some. We've already covered reactions where one carbonyl reacts with 2 molecules intermolecularly to give a ketal or an acetal. What would happen if we take a diol, say a 1,2-diol or 1,3-diol, and react it with our aldehyde or ketone? Presence of acid, we can drive the equilibrium towards a cyclic acetal or ketal. And then if we want to get a little bit more sophisticated, we could have an intramolecular reaction of an alcohol functionality and an aldehyde or a ketal in the same molecule. Initially, of course, like all the other processes, they will give you a hemi-acetal or a hemi-ketal. And if the reaction is allowed to proceed with 2 intramolecular OH groups, then we'll get a spirocyclic system, a system with 2 rings linked onto the same carbon. Let's think about the energetics of this. Well, we started with 1 molecule, we protonated it, and 2 waters were lost. We gained total number of molecules, the entropy of the system increased. Thermodynamics loves that. It's good for the delta G value, so that's a very favorable ketal to form. So in summary, remember the key points, and let me say them backwards. Let's start with an aldehyde or a ketone. In the presence of acid, it protonates on the carbonyl. And then an alcohol molecule attacks the oxonium ion that's formed. The oxonium ion is a tetrahedral intermediate. It transfers a proton to the OH group this time. OR group pushes and water is lost. We form a second oxonium ion, and that's attacked by another alcohol to give us an acetal from an aldehyde or a ketal from a ketone. What would happen if we took our ketal and put it in not water, but a different alcohol? Well, the answer is we'd switch OR groups by just the same type of process. So in water, we form a hemi-ketal, but in alcohol, we form a mixed ketal as an intermediate, two different OR groups. And if we allow this reaction to go to equilibrium by excess OR, then we'll form a different ketal. But of course, the product ketal can't lose water. Only the hydrate loses water. And that's the difference between these two mechanisms. Let's look at that key step again, because it's so important, really. What about the frontier orbitals for this? Well, we've got a non-bonding pair of electrons in a lone pair orbital, a tetrahedral orbital on the oxygen, and that interacts with the lowest energy unoccupied molecular orbital, and that's sigma star for the CO to the other oxygen. You can feel those electrons from one oxygen filling up the LUMO of the other. And as they do, of course, when you put electron density in the LUMO, the bond becomes weaker. But the bond can't quite break until we protonate that second oxygen. So here's the HOMO-LUMO interaction. It's simply stabilizing the oxygens in that orientation with one lone pair aligned with the LUMO of the sigma bond, the sigma star. In the LUMO, we have the sigma star. In the HOMO, we have a filled pair of electrons in an orbital associated with one of the oxygens. Thank you very much for listening. I hope this video helps you with your studies.